Last time we were able to build up our 6502 computer board and connect it up to our FPGA. Now let me ask you a question. What's the first thing you do when you try out a new programming language? You print hello world, right? So let's do it. Let's just compile printf hello world and run it on the 6502, right? Well, sadly, this turns out to not be so simple. Now, the problem lies in that we don't really have a way to print something from the CPU. And of course, if we want to do anything useful with it, we need to be able to print. So back in the day, you had these devices, like you see here. This is an old terminal, and this would basically allow you to send in characters to the terminal and get back user data that the user inputted with that keyboard that you see right there. Of course, that's a very old machine, but thankfully nowadays we have these things called computers that have a lot of uses. And one of these uses is to emulate such a machine. So if you're on Linux and you're an Emacs user, as you should be, you can use the serial term mode, and that will allow you to emulate such a terminal on your own computer. If you're on Windows, you can use a program like PuTTY. Now we have established that we will be using a terminal to communicate with our processor. Let's look at how our pipeline, our communication pipeline, is actually going to look like. So the first thing that we will have is our computer, and this is going to communicate with the FPGA, which is in turn going to communicate with a 6502. Now, how will the PC and the FPGA communicate more concretely? Well, the FPGA board, thankfully, has a chip called an FT board that can convert between USB signals from the computer and the signals that you usually use with a terminal. And of course, between the FPGA and the 6502, this is where the fun part comes in. We're going to have to implement our own way to transfer those signals to the 6502. So now let's have a more concrete look at how the protocol used by a terminal looks like. So this is called a UART Protocol. This is used by two devices to communicate. So let's say we have device 1 here and device 2, and we want to perform communication between the two. Well, we're going to have a wire. This is going to look like an actual physical wire through which device 1 is going to communicate, is going to send data to device 2. And we're going to have another wire through which device 2 is going to send data to device 1. So these are actual physical wires, and you're going to have electrical signals going through them. Now let's have a look at how these electrical signals actually look. So these are conformed by messages where you have a start bit that is going to look like a low signal on the wire, and you have the bits from the least significant to the most significant in groups of 8 bits usually. You can have one more if you want, or a few more, depends on how you set it up, but this is the most common configuration. And then you're going to have one or more stop bits after the data, and this is going to look like a high signal. Now let's say you have this number. This is 130 in binary. So if you wanted to send this through a UART, it will look like this. So the start bit is always low, so it's going to be a 0. Then you take the least significant bit, that's going to be a 1. Then you take the next bit, 1, 0, 0, 0, 0, 0. And then finally the most significant bit, 1. And finally you're going to have the stop bit, which is going to be a high. So that's going to be a 1 as well. So you might hear about RS-232 UART and a TTL UART. So what's the difference? Well, the difference is that when you talk about RS-232, that's a specification that specifies that the signal, so a high is going to be 15 volts and a low is going to be a negative 15 volts. However, when you talk about the TTL UART, that stands for transistor level logic, and that's going to mean that you're going to have highs of 3.3 volts and lows of 0 volts. So now that we've had a look at the UART protocol, let's see how the processor will actually see the peripheral that we will implement in the FPGA. So the processor sees its memory like this. It has RAM, then it has memory that it can access, and when it accesses memory, it can actually interact with the FPGA. So the first thing that we will place there is going to be a data register to interact with the UART. This is going to be placed in the first location that the processor can interact with the FPGA. That is address hex 4000. We're going to be able to read and write this register. And whenever you read this register from one of the lines that is coming to the FPGA, it's going to take whatever data is waiting that was sent from the computer, and the processor is going to be able to read it. And when you write this register, it's going to write data and it's going to send it to the computer. So as you can see, this is quite interesting because we have a single location in memory that the 6502 can access. And whether you read or write it, it changes the behavior of what is actually done. And of course, we want to know a bit about the status of our peripheral in the FPGA. So the next memory location is going to be a read-only memory location. And this is going to tell a bit about the status. And the third bit, so when you read the whole byte, each bit is going to mean something else. And in this case, bit 3 is going to tell the 6502 that there is something waiting. So there is something that it can receive. And then bit 4 is going to tell the 6502 that the FPGA peripheral can actually send, because if the 6502 sends too quickly, then the FPGA itself might not be able to send fast enough. So this is going to make sure that the 6502 can check that it can actually send at that point. Now, of course, we've talked about UARTs and 6502 memory and all that, but we haven't actually talked about the FPGA design. So let's look at how this looks like at a glance. So this is how I have designed the actual FPGA design, digital design. So we're going to have the signal router that is going to interact with the CPU directly, with the 6502 CPU. And it's going to send the CPU its clock signal, its reset signal, and IRQ. Of course, we're not using IRQ right now, but later it might come in useful. And it's going to communicate with the 6502 with data, and it's also going to receive the address. So whenever the 6502 sends data, whenever it writes data to any of those addresses that we talked about, the signal router is going to detect that, and it's going to send that information to the UART interface, which might send it to the computer. So we have the UART interface, which communicates to another part of the FPGA that's going to generate the signals to communicate with the PC, and it's going to do that via queues. So let's say that the 6502 wants to write some data to that memory location. The signal router is going to pass it along to the UART interface, which is going to add that byte to the queue, and the UART module is then going to send the data to the computer. So finally, we've implemented the UART on the FPGA, and we can actually print hello world now with the 6502. Great. So let's look at some of the sample code that I wrote. So let's look at the lines. The first line here tells us that we're using the 65C02 processor. This is a modern version of the 6502. This line just tells where you want the output to go. Then you have this line that tells you that the ROM starts at this address, As you remember from the memory map, that's true. Then we're going to start iterating to the string to print it. First we load X with 0. So the X register is going to be our counter. Then we're going to jump to the plus location here. And we're going to load the A register with the current string location. So it's going to be an H at first. And we're going to jump up here. And this is going to store, this is going to write the current character to the UART register, to the data register of the UART. And we're going to increase X, and we're going to continue until we have a 0 in A. So when it reaches here, it will stop. And then in this next part, it's first going to check, is there something waiting, by checking the status register of the UART. So it's going to load it into A, and then it's going to check if the 4th bit is active. And if it is, then it's going to load from the data register, and it's going to store back into the data register. So this is going to basically tell us if our UART is working. We're going to load from the UART, so any input that comes from the computer, we're going to write it back out to the computer. Now we are actually ready to burn the image into the EEPROM. So let's grab that EEPROM and put it into our burner and actually burn that program. I have compiled it to a binary file, and it is now ready to be burned. So here we have our terminal. Let's use the Mini Pro to burn to the EEPROM. Now let's put that EEPROM back into the FPGA. Oh, the FPGA expansion board, to be more specific. Now let's test it out. So there we have it. Hello world from the 6502. And if we type in anything, there we go. Perfect. Well, thank you for joining me in this small adventure that you have witnessed, trying to get our 6502 computer to print out Hello World. Now you can appreciate all that is necessary just to get that to happen. Of course, I will upload all of the Chisel FPGA HDL, the hardware definition language that I used to program the UART on the FPGA. And stay tuned, because next time I will be installing BASIC on the computer. So this is a programming language that will allow us to do much more with this computer. Until next time.